So let R be a vector-valued function. We're using vector-valued functions to track moving objects in space. We're going to define three vectors related to your vector-valued function. We're going to define capital T to be the derivative of your vector-valued function divided by its length. This is known as the unit tangent vector. We've seen that the derivative of your vector-valued function is a vector that's tangent to your curve. If I divide by the length, that makes it a unit tangent vector, a vector of length 1 that's tangent to your curve. We're going to define capital N of t to be the derivative of this function, the derivative of your unit tangent, divided by its length. This is known as the unit normal vector. And later we'll describe why the unit normal vector is always at a 90-degree angle with the unit tangent vector. So we'll show that later. A third vector is b of t. This is defined to be your unit tangent vector cross your unit normal vector. And this is the unit binormal vector b. The unit binormal vector. Since I'm defining the unit binormal vector as a cross product, it's automatically at a 90-degree angle with both t and n. Okay, let's do an example first of calculating these three vectors, and then after that example, I'll explain why we're doing this and who even cares. So here is an example. Let's find t, n, and b for the helix r of t, which is cosine t, sine t, and t. So my helix is a vector-valued function. Let me draw a picture of the helix. It's a curve that's moving in space in the shape of a spring, twisting up around the z-axis. So here is my three-dimensional axis system. Here's x, y, and z. The curve vector-valued function cosine t, sine t, t spins around in a circle in the x and y axes while moving up the z-axis, creating a spring-type shape. It's curving around like this. So there's my vector-valued function. The unit tangent vector is the derivative of your vector-valued function. So negative sine t cosine t 1 divided by the length of that vector, the square root of sine squared t plus cosine squared t plus 1, which is 1 over the square root of 2 times negative sine t cosine t 1. So there's my unit tangent vector. My unit normal vector is defined to be the derivative of this divided by its length. So the derivative of this vector would be negative cosine t, negative sine t, 0. I have to divide that vector by its length. So factoring in the square root of 2, I think the length of that vector is negative cosine t over the square root of 2 squared plus negative sine t over the square root of 2 squared. And I think if you simplify this, you simply get negative cosine t, negative sine t, 0. And then lastly, the unit binormal vector b is t cross n. So you do the cross product calculation, ijk. You put the vector t here. So this vector in the middle row would be t, In the bottom row, you put n. Then you calculate the cross product. I'm going to skip the calculation now for the sake of this video, but it's not a difficult cross product calculation if you know that. And in the end, you will get 1 over square root of 2 sine t, cosine t, negative cosine t, and 1. So here's an example of the unit tangent, normal, and binormal vectors. If you put in different values for t, you get different vectors. Let's see what happens at t equals 0, say. So at t equals 0, I plug in 0 for t, and I get the unit tangent vector is the vector 0, 1 over the square root of 2, 1 over the square root of 2. On my picture up here, what this is doing for me is the following. So here at the picture, the red dot is the value of the curve when t is equal to 0. So I get that value at t equals 0. The unit tangent vector is a vector in this direction. So if I plot a vector in this direction, I get the vector t as shown. It goes to the right and up somewhat. Unit tangent vector, tangent to the curve. The unit normal vector turns out to be negative 1, 0, 0. So the unit normal vector is pointing in the direction of the negative x-axis. So there's my unit normal vector, n. The unit normal vector and the unit tangent vector are at 90-degree angles from one another. And the unit binormal vector, b, is equal to, let's see here, 0, negative 1 over the square root of 2, and 1 over the square root of 2. So it's going no component in the x direction, but it's going in the negative y direction and up. So there's my unit binormal vector. If I plotted b, n, and t at a different point, I would get a different three-axis system. So if I plotted the t, n, and b up here, it might look like this. T is tangent to the curve, n is normal to the curve, and b is sticking straight up. So what this is doing is creating a three-dimensional axis system that moves along the curve. So at any point on the curve, you have a different three-dimensional axis system for your use. So imagine that this curve is the path of a spaceship traveling from Earth to Mars. If you fix an axis system on Earth or on Mars or even in the sun, the path of the spaceship is going to be an immense calculation because the Earth is spinning around its axis, it's traveling on a path around the sun. Same thing with Mars. So if you put your axis system on Earth and watch how that changes with regard to the path of the spaceship, all the calculations are going to be immense. Instead, a thought is create an axis system that moves along with the spaceship. Therefore, calculations could be a lot easier. So we'll see how that happens. Now, to end this video, I'd like to show you the reason why the unit tangent and the unit normal vector are actually perpendicular at 90-degree angles. Well, it's definitely true that the length of the unit tangent vector is 1. So the length squared, the magnitude squared, is 1. That's because we designed the unit tangent vector to have length 1. So the magnitude squared is the dot product of t with itself. So differentiate both sides. Remember, capital T is really a function of little t. I didn't put the argument in here, but there's real little t's involved on this side of the equation. So I'm going to differentiate with respect to t. And if you do that, the derivative of this side is 0, where the derivative of the right side you can calculate using the product rule for the dot product. So we saw in our previous video that you could take the derivative of a dot product using the dot product rule, which is the product rule you learned in Calculus 1, just extended to dot products. So the derivative of t times t dotted with t plus t dotted with t prime. So that says 0 is equal to 2 t prime dot t. In other words, the dot product of t prime with t has to be 0. The unit normal vector is in the direction of t prime. So this is in the direction of n. And of course, t is in the direction of the unit tangent vector. The dot product is 0. That's exactly what it means to be at 90-degree angles. So that's the algebraic reason why the unit normal and the unit tangent are at 90-degree angles. The geometric reason is that the unit tangent vector is a unit vector, always length 1. So it moves around, but always has length 1, meaning the unit tangent vector traces out a curve on a sphere. And if you think about it for a minute, any tangent to a sphere has to be perpendicular to the radius of a sphere. So that's the geometric reason why this holds. Okay, so what we've done in this video is taken a vector valued function and defined 3 related vectors, 3 related vector valued functions, t, n, and b. They create a frame that moves along in space along with your curve. I'll show you some computer simulations, some computer generated images of what's happening in the next video. All right, I'll see you there.